All right. So the other sort of expansion to this in this section is solving what we call rational equations. And so these would be, equations made up of like rational terms. It's essentially, they're kind of, they're not super complicated. I guess they would be, I don't really have a standard form for it. So equations where the terms are rational expressions. So that is right. Rational expressions meaning kind of fraction expressions. And so I'm going to do a couple different variations. The strategy to sort of solve this is going to be pretty consistent. And so what we're going to do to solve is, so find an LCD and rewrite all the terms over that LCD, right? So find a common denominator. And so that is across, not just on like side to side, although you can do that, but really across all of your terms from both sides. So you're going to look at, 2, 3, 4, 5, maybe different like terms and find a common denominator across all of them. And then you want to rewrite the equation so that each of the individual terms is over that common denominator. You're going to need to exclude any x values that make the LCD equal to 0. This is sort of the same thing as your, restrictions. From P6, anytime you have, right, a rational expression, anytime you have variables in the denominator, you need to make sure that you don't, you kind of make a note of any of the x values that would sort of make that denominator 0, right? We're not allowed to divide by 0. Kind of one of our fundamental math rules, sort of breaks our equations. In P6, we kind of just were saying that. We weren't really doing anything with the values, right? We just were like, hey, notice, right, the x can't be equal to this, this, or this. Now that we're trying to solve an equation and we're actually trying to find x values, right, whatever x is equal to, now the stakes are kind of real, right? Because, if I'm trying to find an x value, but then that's the kind of value that would actually make the bottom of my equation 0, everything kind of like comes apart. So I definitely need to know about that. Step 3 here is, at least the way I kind of like to do this, what some people will say is you kind of multiply everything by the common denominator, and the idea is that actually cancels everything out. That's kind of the most mathematically kind of like true way to sort of say and do that. Visually what I would say is what it looks like is if you have everything written over the common denominator, you can clear away the LCDs and solve your equation based on the numerators, right? So the idea here is if you rewrite everything over the same common denominator, then that means the whole equation is kind of balanced in essence, right? It sort of is all written over the same values, which means that, your denominator, if all of the denominators are the same, then that means they're not really having an impact on the solution, right? Because it's all perfectly balanced. And so to solve it, all you need to do is look to the numerator. So you can literally rewrite the equation with no denominators, rewrite it sort of not as a rational equation at all, but essentially just rewrite it as a linear equation and solve it from there. So let me give you a few examples, and I'm actually going to start with one that is technically not a rational equation. So let's do x over 4 equals 2 plus x minus 3 all over 3. So what we can do is we can say, note, this is not technically a rational equation. Really what this is, it's just a linear equation, like with some fraction terms. But that's fine. We're actually going to use the same strategy. So that's why I'm sort of doing it here anyway. So we're going to use the same strategy. As with our rationals. But the thing here that's going to help is our denominators. So in this case, finding a common denominator. So this is kind of x over 4. This is 2. You know, the idea here is maybe write that as 2 over 1 plus the quantity, right, x minus 3 over 3. So finding a common denominator here is really just going to be finding a common number denominator. I don't have any variables in the denominator. So that's the difference between this technically being a rational equation. You would need to have x values in the denominator to be a true like rational expression or rational equation. This is technically just sort of a linear equation. You know, this would be kind of a 1/4 x equals 2 plus, 1/3 x minus 3 over 3, right? If you were kind of splitting it up. We could do that, but I think doing this common denominator stuff is going to be best. So our values here on the bottom right, 4 and 1 and 3. The LCD there would be 4 times 3 would be 12, right? So what I'm going to do is rewrite this equation. I'm going to leave myself a little bit of space. I'm going to throw parentheses there to sort of get everything here to 12. So what's missing? Well, to get from 4 to 12, I need to multiply by 3. 2 over 1, right? I mean, the 1 is the denominator, so I need the full 12 there. So times 12 and times 12. And then here's 3, so what I'm going to need is a 4. And so just like, right, when we were trying to do stuff like add these rational expressions together, you have to find a common denominator and then get everything in sync before you can kind of add and combine, right? You kind of get these kind of ramifications from your multiplication on the bottom. You get these ramifications up top. So this becomes kind of a 3x over 12 equals, right? 12 times 2, 24 over 12 plus, and we can even just sort of call this 4 times quantity x minus 3 over 12. So that's what we get. I need to sort of check, right? Make sure my LCD is not equal 0. That's always true, right? There's no x's there. So there's no restrictions. If we have a true rational equation, there'll be x's there, of course, and then you'll have to actually get some restrictions. So take a note of that. Once we've done that, however, I can just clear the 12 out of there, clear my LCD, and what I'm left with is then just 3x equals 24 plus 4 times x minus 3. Right, so that's 4x minus 12, right? Now I'm just doing regular linear equation kind of moves to solve this. So 3x equals 24 plus 4x minus 12. Running out of space a little bit here, right? 24 and minus 12 would leave me with a positive 24. 3x equals, right, plus 4x. And I guess let's maybe move this 4x over to the left. And then we can just leave the 12 in place. Sometimes what people like to do is this questions of should I bring the x's to the left or to the right, or does it matter? And the answer is it doesn't really matter. All things equal, in theory, I kind of like to try to move stuff such that you get a positive x term. this is going to give us a negative x term, right? This would be sort of negative 1x equals the 12 that's here. That's also okay, right? Because if you have a negative 1x, you know, how do you get rid of it and sort of solve it for positive x? And the answer is, well, you just divide by negative 1, right? Which is really just going to be kind of a flip. So a positive x in this case would just equal negative 12, right? If negative x is equal to positive 12, then positive x is equal to negative 12, right? This is sort of flipping just the negative back and forth from one side of the equation to the other. And that's totally fine. The LCD here, right? No x values on it, so there's no restrictions. You know, again, technically this is kind of a linear equation. It just has these fraction terms. I'm going to pause this one here. We'll do a part 2 on this where we actually do a couple examples with the x variable in the denominator. So that'll make it a little more complicated. So see you in the next video where we do that.